Good evening, class. We are looking at college algebra practice test number 3, covering chapters 5 and 6. Here, chapter 6, exponential and logarithmic functions. Again, as always, we have the pledge, meaning everybody's supposed to take the exam on their own. All right. Find the formula for an exponential function that passes through points 0, 2000 and 2, 20. And the function has the general format a b to the power of x. And by the way, we're going to discuss this exponential functions in general shortly. So this is the function, and basically you have two pairs. This means f of 0 is 2000. This means f of 2 equals 20. So we are going to write 0, 2000 means f of 0. So I'm going to replace the x with 0. A times b to the power of 0 is 2000. That's the meaning of it, everybody. And this one, 2, 20, that means I replace the x with 2, y, or f of x with 20. That's the meaning of it. So if we look at this one, b to the power of 0 is just 1, which makes a 2000. So let's replace the a here with 2000. So we are going to replace the a with 2000. So f of 2 is 2000 b squared equals 20. So clearly, can drop the 2000 by dividing both sides. We get 1 over 100, and therefore b squared is 1 over 10, negative 1 over 10, and it's important to remind everyone. So we have two answers. Negative is out. The base for exponential functions is positive, okay? Can't be 0, can't be 1. And so the function f of x is 2000 times 1 over 10 to the power of x. And as always, you can check. Simply put 0 here. It should give you 2000. If you put 2, you get 1 over 100, right? Because you square it times 2000. It should give you 20, and it does. And that's the idea. Liz deposits $10,250 into an account that earns 4% compounded interest. How much will the account have at the end of 10 years if it is compounded monthly, where A of t has this formula? I'm going to remind you, this is the formula for compound interest. For simple interest, I equals PRT. P is the principal, R is the rate, T is the time. For compound interest, P times 1 plus R over N to the power of NT. P is the same P, principal. R is the same R, rate. T is the same T, time. N is the number of times compounding takes place per year. So let's write the given. So this one is a P. The principal is $10,250. This is 4%. The rate is 0.04 over the course of 10 years. So let's write that first. And then we move on to the next step. For monthly, N is 12. Okay. So $10,250, 1 plus 0.04 over N times 10. And for monthly, as I mentioned, N is 12. So now replace. Put it into a calculator. And because we are dealing with money, go with a couple of decimals, $50,281.03. Let's do the same thing, but this time weekly. So when we go back to this one, we replace the n with 52. So n, replace it with 52. Again, put it into a calculator. Gives you a little bit more. $15,288.85. Now, how much will the account have at the end of 10 years if it's compounded continuously? The formula is A of t equals P e to the power of R10, P e to the power of RT, where we have the same P, the same R, the same T, and E is the base of a natural log, 2.718, and it continues indefinitely. So we replace the P with 10,250. E is an exact answer. R is 0.04 and T is 10. So the product of these two, of course, is 0.4. E to the power 0.4 times 10,250 gives you a little bit more, $15,291.20. So compounding as we add to n and this becomes indefinite, produces more in return. So let me erase my work. And so when it comes with compounding, when it comes with continuous compounding and so forth, or not necessarily continuous compounding, we can discuss doubling time. Doubling time, by definition, means how long it takes for whatever you have. In this case, we have the principal of $10,250 to double up. Okay. And so, in essence, you really don't need to know what P is because this becomes 2 times P and you can drop it regardless of what this number is. So you don't even have to know what that is. And since you want to solve for T, you're going to take the natural log. Left side becomes ln2 and the right side becomes RT. Therefore, if you're solving for T, ln2 over R, and by any chance, if R was missing and it's not, it's ln2. Okay, over T. So ln2 divided by 0.04, putting it into a calculator, gives us a little bit more than 17. It takes more than 17 years, 17.328. I put a lot of decimals. You should always put a lot of decimals unless asked otherwise, okay? And so that's the idea. Now, let's look at exponential functions in general. So we are given a bunch of graphs. Use the graphs shown to answer the following question. All have the form f of x equals ab to the power of x. Okay, so first let's discuss the graphs in general. Never mind this one. So the formula y equals a to the power of x. In this case, the base is b, the base is a, the base is anything that you want. This one is an exponential function. It's an exponential growth. And a, the base, is larger than 1. This one, a is between 0 and 1. In general, a can't be 1, and it must be positive. So we write, when y equals a to the power of x, a must be positive and a can't be 1 because 1 to the power of x is 1 and it becomes a horizontal line. Domain, I hope you see that the domain is all real numbers. Range, it can go from 0 to infinity. It can't even, this is a horizontal asymptote. So this comes along the x-axis this way and that one that way, 0 to infinity. HA, short for horizontal asymptote, has the equation y equals 0 because the x-axis has the equation y equal to 0. And clearly this point is located at 0, 1. That is the y-intercept of the function. As I mentioned, this function is an increasing function. exponential growth. This function is a decreasing function, exponential decay. As an example, if we have a 2 to the power of x versus 2 to the power of minus x, they are symmetric with respect to the y-axis, okay? And of course, this is your horizontal asymptote, y equals 0. Now, what happens if we look at different functions with different base? As an example, y equals 2 to the power of x versus y equals 5 to the power of x versus y equals 0.5 to the power of x. When the base gets larger, and of course we are talking about the positive value, it's on the right side, positive value on the right side, and it gets closer and closer to the y-axis, the base is larger. On the left side, okay, 0.5, okay, and it gets smaller as it gets closer and closer to the y-axis. So for this one, which graph has the largest value of b? And again, I want to show you also this one. In general, y equals ab to above x. In other words, this one doesn't have anything in front of it, this one doesn't, but if it has one thing, something in front of it, the result is very simple. If you replace the x with 0, this goes to 1. Therefore, this location, which was 0, 1, 0, 1, 0, 1, now it's at 0, a. That is the difference. So if you have an a in front, it just changes the location of the y-intercept from 0, 1 to 0, a. Now, which graph has the largest value of b? We discussed that here, just for the sake of argument. This one is larger. If you look at this one is larger than this one. So that would be the one that it's closest to the y-axis on the right side, okay? So when you look at these functions, okay, which one is closest to the y? First of all, the right side. So you look at this one, this one, this one. This one is the closest to the y-axis. So the answer is clearly graph D. On the other hand, which one has the smallest value? Now, the same thing, closest to y, but this time from the left side, because it makes it negative, okay? And so on the left side, we have this one, we have this one, we have this one. This C seems to be the closest one. Now, which one of them has the largest value for a? Notice, again, as we mentioned, f of x equals a b to the power of x. The y-intercept changes from 0, 1 to 0, a. So all of them have the y-coordinate, the y-intercept at 0, a. And so that's the meaning of that, first and foremost. So let x be 0. Y-intercept is located at 0, a. So the largest a, the largest y-intercept. And clearly, here's the y-intercept, here's the y-intercept, and here's I hope you see that this one, there is no other one having a larger y-intercept. So this one, therefore, the answer is C. For the smallest one, we are looking for the smallest. So that's the graph C. Graph C. For this one, we are looking for the smallest a or y-intercept. And again, look at this one, this one, this one. This is the bottom one, okay? And this graph is graph F. So that's how we distinguish among those. So having said that, let's quickly recap so we understand what's happening. Number one, y equals a to the power of x, a general form of an exponential function. This is increasing when a is larger than 1, decreasing when it's between 0 and 1, and the y-intercept is at 0, 1. So a must be positive, a can't be 1. Domain is all real numbers, range is 0 to infinity, and the x-axis, which has the equation y equals 0, is the horizontal asymptote. This indicates as the base gets larger, the function rise up faster, gets closer to the y-axis. And this one says if we have a in front of it, the y-intercept of 0, 1 moves to 0. That's it. Now, we want to use transformation. So use transformation of the graph of f of x equals 2 to the power of x of the function. Below state the horizontal asymptote, the domain, and the range. So we should know y equals 2 to the power of x. If I said 3 to the power of x, 5 to the power of x, 10 to the power of, it looks almost like that. Okay. And with that, the y-intercept is at 0, 1. Okay. Again, remember from the previous page that the x-axis y equal to 0 is a horizontal asymptote. This is an increasing function, domain from negative to positive infinity, range from 0 to infinity, 0 is not included, and so all of the above. Now, when we want to go with 2 to the power of minus x, when you compare this, we're going to change the x to minus x. That is reflection with respect to the y-axis. So this is 0, 1. This is reflected with respect to the y-axis. Looking like that, same y-intercept. The graph is f of x equals 2 to the power of minus x. So everything is the same as this guy except it's decreasing, meaning for this function, horizontal asymptote is the same as the x-axis y equal to 0. Y-intercept is the same, 0, 1. There is no x-intercept. Domain for both of them are real numbers. The range for both of them from 0 to infinity. And take a look. By the way, 0 is not included. So everything is the same. What is the difference? Increasing. Y equals 2 to the power of x is an increasing function, exponential growth. 2 to the power minus x is a decreasing function. Okay. By the way, just for the sake of argument, I want to make sure that everybody understands that this could be 2 to the power of negative 1 to the power of x, or 1/2 to the power of x. That's another way of representing it. It means absolutely the same thing. Now, we want to graph g of x equals 2 to the power of x, this function, plus 1. So that means shifted up by 1 unit. So if I take it 1 by 1 unit, what happens? This shifts up by 1. The horizontal asymptote goes up by 1. So we have this horizontal asymptote. This is y equals 2 to the power of x plus 1. This is the horizontal asymptote. And this is the new location of the y-intercept. So this is located at 0, 1. Now this is located at 0, 2. Horizontal asymptote y equal to 0. Now y equals 1. What about the domain? The domain doesn't change. Or look at all three, all real numbers. But the range over here is from 0 to infinity, but now it stops here. So from 1 to infinity. So the difference is the range is no longer the same. So I hope it's clear to everybody. Consider the function f of x equals 4 to the power of x, right? A function that results from a given transformation. Shift f of x 3 units up. So simply put, add 3. That's g of x equals 4 to the power of x plus 3. Part B, shifted 5 units left. So we are going back to original one. You want to shift this one, not this one. This one. So replace the x with x plus 5 because you're shifting it to the left. Going back to here, reflected about the x-axis. When you reflected about the x-axis, this becomes that. That means you put a negative in front of it. You negate the function, the y-axis. Reflected about the y-axis, then this is the y-axis. If you assume x is positive, then minus x is negative. Okay, and by the way, we can't. So in general is x. And that means x changes to minus x. So in this case, I of x equals 4 to the power of negative x. So that's the transformation. Now, the graph is transformation of f of x equals to power of x. Write an equation for the graph shown. So you may recognize it as, an exponential function as it's given, but let's come up with a couple of easy things that will help us. One of them, obviously, the y-intercept is at 0, 2, and you can see that you can draw the horizontal asymptote, and that has equation 1, 2, 3, y equals 3. So let's start with a graph of f of x equals 2 to the power of x. We know it looks like that, and obviously this one is located at 0, 1. And so since this goes down, let's flip this over. So to flip it over, this becomes negative minus 2 to the power of x, reflected across the x-axis, looking like that. And so 0, 1, now it becomes 0, negative 1. And in both cases, of course, as you can see, the horizontal asymptote is not changing. The horizontal asymptote remains for 2 to the power of x as well as minus 2 power of x as the x-axis of y equal to 0. Now, I hope you see that this looks like this, but y equals 3, that means shifted up by how many units? By 3 units. Let's go up by 3 units. And so it's y equals 3, that is the asymptote, the new horizontal asymptote, and 0, 2 is the new y-intercept. Therefore, we are going to say the function is this function shifted up by 3. That means plus 3. So h of x is negative 2 to the power of x plus 3. That's how we got it. If we happen to have the same scale, we see that they will be absolutely identical. Logs, if b, the base is larger than 0, and it can't be 1, then y equals log x base b is equivalent to x equals b to the power of y. We have this here. X equals b to the power of y, y equals log x base b. Notice they have the same exponent, the same base. One way to follow that, I'm going to put an arrow here and take a look. If you follow the arrow b to the power of y equals x, and if we can go from logarithmic format to exponential format and vice versa, basically we're done. Because the idea is to be able to go from one format to the next. Easy. So a common law, a general law, y equals log x base b, that means b to the power of y equals x. And with that, we get the following properties. Log 1 base b is 0. Look at this arrow. B to the power of 0 is 1. Log b base b equals 1. Now, let me explain number 2. Number 2 says when the base and the argument are the same, this is called the argument of log. And this is obviously the base. When the argument and base are the same, the answer is 1. That's all it says. Look at this one, the same thing here. B to the power of x is b to the power of x. Now, I have the proof for those. And by the way, these two refer to b to the power of log x base b equal to x. You can look at it. And what it means, logarithmic functions and exponential functions are inverse functions. Number 5 is called the product rule. Log xy base b is log x base b plus log y base b. Log of x over y base b is log x base b minus log y base b. Log of x to the power of n base b is n log x base b, and n, in other words, comes and sits in front, becomes a coefficient. This is the general case with any base, as long as that base is positive and it's not 1. Now, as you know, in the case of a common log, the base is 10. So y equals log x. See, we don't write this. I just write it so you know that means this, log x base 10. That means 10 to the power of y is x. And now here's the rules. I put them as a number so you can see. First of all, let me erase my work. Look at the first one. All you have to just drop the base. Look at this one. We want the base and the argument to be the same. When we don't have a base, the base is 10, then it must be log 10. This one, b to the power of x, that means 10 to the power of x. This one is the same as, remember, b is 10 here, that's why. And for the rest of them, 5, 6, 7, just drop the base b. Just write log and you're done. So these are properties of logs. Hopefully everybody is familiar with. Natural log, y equals ln x means log x base b. We don't write it in this format. This means the base is e. In other words, e to the power of y is x, and it gives rise to these properties. Remember, instead of log, we're going to write ln1. Now, log b base b, if these two must be the same, and we know ln means the base is e, that means ln e. This one, the base is b. This one, when we write ln, we know it's e. So these two, 3 and 4 again. Let me just make sure everybody understands that 3 and 4 refer to the fact the functions, logs, and exponentials are inverse functions. 5, 6, 7 is just like that. Instead of log, just write ln. Okay? So the two functions are inverse of each other. Therefore, if you graph them with respect to the line y equals x, they are symmetric. That means y is e to the power of x, y equals ln x are symmetric with respect to y equals x. And so this is called the change of base formula. Log x base b is log x over log b. Choose any base, for example, a. But obviously, we want to evaluate it. We use either common log or natural log. We are not saying log x equals ln x. We are saying the ratio of log x to log b is the same as ln x to ln b. And of course, you can do the cross product. Okay. For example, if you multiply these two, you get this one. Log x base b times log b base a is log x base a. In other words, if you write it in this fashion, and this argument is the same as this, you can continue indefinitely. You get the final argument with the very first base, and that comes from the change of base formula. And finally, if I look at this point, it's located at 1, 0, which is the x-intercept of ln x. And if you go to the left of that, here is negative. ln x is negative between 0 and 1. And 0 at x equals 1. And it's positive for x larger than 1 for this. It's extremely important that we know this stuff, okay, because they're not going to go anywhere, okay? Okay. Rewrite each equation in exponential form. Let's do this. 5 to the power of q is m. I don't have a base, ln, that means the base is e. E to the power of z equals v. I don't have a base, that means with log, the base is 10. 10 to the power of t is w. So just follow the arrow. Rewrite each equation in logarithmic form. 3 to the power of x is y. That means log of y with base 3 is x. That means log of h with base e is k, so therefore we write ln h equals k. Log of b, base 100 is a. That's not a common log. The base is 10 for common log. This is not the case here, everybody, okay? All right, state the domain, vertical asymptote, and the end behavior of the function. F of x is log of x minus 7. And I want to first remind you that the general graph looks like that. Log x base 2, log x base e. This is ln x, log x base 10. On purpose, I'm writing the bases because I want to make a point. This base is 2, this base is 2.718, this base is 10. As the base gets larger, then the function doesn't rise as fast. So smaller the base, the faster it rises, but they all have the same x-intercept located at 1, 0. So y equals log x base a is positive, a can't be 1. Domain is from 0 to infinity, range from negative to positive infinity. Vertical asymptote is the y-axis, which has the equation x equals 0. If you remember the graph, you remember all the information that is mentioned here. So any log with base a must be positive and it can't be 1. Domain from 0 to infinity, 0 is not included. Range from negative to positive infinity, VA is x equals 0. I hope you remember when we discussed inverse functions, domain of one becomes range of the other. So compare it to exponential functions. And of course, in this case, because a is larger than 1, it's an increasing function. What happens if a and a is not 1? So in this case, a is larger than 1. What happens if, so maybe I should write this. Do I have it somewhere? No. For this case, oh, we have it here. Now, what happens when a is between 0 and 1? Then it goes this way. Okay. So look at this one. A is between 0 and 1. It's a decreasing function. As an example, y equals log x base 1/3. Let me erase my work. So this format, the base is larger than 1, and this one. For example, if I want to graph log x base 1/2, it will flip over with respect to the x-axis. Okay, just to let you know. So I wanted to remind you how the log looks like. And in this case, the base is 10. So basically, we are looking at the blue one, something like that. And of course, in this case, we have the same x-intercept at 1, 0. Okay, just reminding you. Now, what happens with this x minus 7? So we go from x to x minus 7. So it shifts right by 7 units. So move this one to the right by 7 units. And originally, the x-intercept is at 1, 0. And now the new one is located at 8, 0. We had the vertical asymptote, the y-axis, but the vertical asymptote, you can set this equal to 0, x equals 7. That will give you the vertical asymptote. So we have the new x-intercept at 8, 0, the new vertical asymptote with the equation x equals 7. Now, let's discuss the domain. Let's discuss the range. Domain is from here to infinity. That means from 7 to infinity. But the range for this one or that one makes no difference, all real numbers. The end behavior, okay, as x goes to infinity, so does y or f of x. As x goes towards 7, f of x goes to negative infinity. What I want to add is this, everybody. This is coming up in calculus. As really x approaches 7, and this is 7 from the right. I want to make sure everybody understands what that means because it's coming up in calculus. Here's number 7, everybody. The left side of 7, we write 7 from the left. That means number is less than 7. The right side, we write 7 from the right. So it's really wrong to say 7, but 7 from the right. So I want to make sure that is completely understood so we can move on. Okay. So x approaching 7 from the right. That is a better way of writing it. 7 from the right. I can't really emphasize this enough. Again, we'll see that in the next course, and I don't want any confusions. State the domain, vertical asymptote, the end behavior for this function, part b, g of x equals ln of 2 minus x. First and foremost, ignore that, and let's go with y equals ln x. And ln x has a x-intercept at 1, 0. So let's start with ln of minus x. Okay. So that means you're changing x to minus x. So you reflect it with respect to the y-axis. So this flips over. And so the x-intercept, which was located at 1, 0, now goes to negative 1, 0. So this was the x-intercept. Now it's the new one. 1, 0 goes to negative 1, 0. Now, so we have this one. This is how you approach it. How do we change it to this one? First and foremost, I'm going to rewrite this, okay? So you understand what happens. I'm going to write it as minus x minus 2. So please understand let me use it. If I plug in, if I distribute, I get minus x plus 2, which is identical to this one. But this will explain the concept of negative and then positive 2 here, which becomes negative. That means it shifts to the right by 2 units. So shifts right by 2 units. So we have this one, then this one. Now we go to the right by 2 units. And as we move to the right, this one, negative 1, 0 to the right by 2 units, 1 and 2 brings us back to the same x-intercept. Okay, everybody? And we can draw the vertical asymptote, which has equation x equals 2. Let me again show you how you find that in general. If they just say, find the vertical asymptote, set 2 minus x, set the argument equal to 0. That's what they want. Just set this one, 2 minus x equal to 0, which gives you x equals 2. So if they ask, what is the asymptote, vertical asymptote, and nothing else, set the argument equal to 0. So what happens here? So we are looking at this one. The domain, what do we cover along the x-axis? From negative infinity all the way to here, to 2. The range doesn't change. For all three, the range is all real numbers. The end behavior, when x goes to this way, okay, x goes to negative infinity, y goes to positive infinity. And x can go all the way to 2 and no more, it stops there. So as x goes to 2, g of x goes down to negative infinity. And again, I want to make sure we understand this is wrong. Number 2, the left of it, we write x approaching 2 from the left. This doesn't mean negative. 2 from the left like 1.99999. 2 from the right like 2.00001. Something very close to 2 either from the left or right. So you want to pay attention to this. This is coming up in the next course, and we want to make sure that we understand that, everybody. State the domain, vertical asymptote, and the end behavior for this function. H of x is minus log 3x of 3x minus 4 plus 3. And we start with log x. Obviously, the base is 10. So y equals log x. We know the graph looks like this. And we know this point has coordinates 1, 0. So that's what we start. So from here, you see the 3x. So we are going to go, so this is 1, 0. We're going to go to log of 3x, which means horizontal shrinkage, okay, by a factor of 3. Okay, what does it mean? It means now 1, 0 shrinks by a factor of 3. So it goes this way and it becomes 1/3 0. So this is the graph. This was at 1, 0. Now it's at 1/3 0. So that's log of 3x. Now 3x minus 4 is the same as 3x, 3 parentheses x minus 4/3. So 3x minus 4 is the same as 3 times x minus 4/3. Well, are we writing it like this? That means clearly x minus x, if x changes to x minus 4/3, we shift it to the right by this much, by 4/3. So we're going to look at this green one and shift it to the right. By 4/3, that means 1/3, comma 0. 1/3 and 4/3 is 5/3, comma 0. So it shifts to the right. And this point now has coordinates 5/3, comma 0. Very straightforward. So again, a quick recap. Here's log x. 3 shrinks the graph along the horizontal axis, minus 4/3, moves it to the right. And now we're going to apply the negative. So we're going to write the same thing here or the same thing here with a negative in front of it. When we do that, it reflects it. So we are looking at this one, this last one, across the x-axis. So reflection across the x-axis. So this graph becomes this, which means the x-intercept remains at 5/3 0. So we have this. What is missing? Plus 3. So now this one shoots up by 3 units. So shifted up by 3 units, and you get this graph. So this moves up, this one. Just move it up by 3 units. And so 5/3 0, the location becomes 5/3, comma 3. So this is the function. This is the graph. And here's the location, 5/3 3. Okay, now let's discuss everything about that. So the graph, we're going to continue. The graph looks like this. We have 5/3 3. We have our vertical asymptote. And the way you come up with the vertical, if they said come up with the vertical asymptotes and nothing else, just set this argument equal to 0, 3x minus 4, and x becomes 4/3, just in case. This is the fastest and easiest way to come up with that. You have the final graph. You can see the domain and range as follows. Domain from here to infinity, that means domain from 4/3 to infinity, 4/3 is not included. Range, we don't have a restriction. It doesn't look like it, but it goes from negative to positive infinity. Now, the end behavior, okay, as x moves towards positive infinity, it's going down to negative infinity, the y, or in this case, h of x. As we approach 4/3, but this time 4/3 from the right of it, then it blows up to positive infinity. So we write, as x approaches 4/3, h of x goes to infinity. And as x goes to infinity, h of x goes to negative infinity. And as I mentioned here, from the right side, x approaches 4/3 from the right, not just 4/3, because really they do have a different meaning. From the left, the function is undefined. From the right, it approaches infinity. That's the idea.